Welcome to this tutorial for the CE150 lab. In this tutorial, we'll be going over the Excel Solver add-in. This is a very useful add-in for engineers, and it's required for this week's assignment. Let's start by taking a look at a simple Excel function, y equals 5 plus 2 to the power of x. This is just a simple function we made up so that we can play with Solver. In this equation, y is our dependent variable and x is our independent variable. We have our function entered in cell C7, as we can see here, and we can see it in our formula bar. We have x, our independent variable, pointed at cell C5. So when we enter a value in C5, we can see the corresponding value of y. Now that's fine, and that's how Excel works. But let's turn this around. Suppose we wanted to find a certain value for our independent variable that gave us a specific value for y. Well, in that case, we'd have to start guessing. Let's say we wanted a final value for y of 11.2. Well, we can see that 3 gives us 13, and 2 gives us 9, so it must be between there. Let's try 2.2. Nope, that's not getting us to 11.2. How about 2.8? Nope, that's much too high. 2.7. Still too high, but closer. We could keep guessing like this and guess closer and closer values until we got to a satisfactory value. But there's a much more easy and precise way to do it than this. This is using the Excel Solver add-in. So let's take a look at that. The default installation of Excel does not come with the Solver add-in installed, so we'll have to install it. In order to do that, we go over to File. Then we'll go down to Options. Then we'll go to Add-ins. Down here we can see Manage Excel Add-ins, so we'll just click Go. And here we have the Solver add-in. Let's click it and click OK. Now when we go up to our Data tab, we can see that the Solver add-in has been added for us. Let's click it. Here we have the Solver add-in primary screen. Solver does a lot of things, and we'll only be looking at one of them in this tutorial, but it would be worth your while to get to know Solver because it can really be very useful. Solver can find the maximum or the minimum for a certain function. A lot of functions have maxes and minimums. The one we're using doesn't. Or Solver can find a specific value. Now remember, we're looking for a value of y of 11.2. Solver can find that for us if we set our objective, and that's going to be your formula. This is the value we want to match 11.2. And we want to set that by changing the value of our independent variable. When we click Solve, Solver comes up with an answer. Let's click OK and see how it did. Solver very quickly and very easily found the value of the independent variable that gives us the value of y that we were looking for. This is much simpler and much more precise than just doing a lot of guessing. Now let's take a look at this week's exercise in Excel. Exercise 2 is determining the composition of an unknown gas mixture. This is the gas mixture that you created by bubbling two different gases through a beaker of water and let the dissolved oxygen concentration come to equilibrium. Let's do a quick review of the equations that we need to get this value. These are the equations that are given to you in this week's assignment. To begin with, we measured the dissolved oxygen concentration at saturation in milligrams per liter. Using the relationship shown in the top equation, we can convert this to moles per liter. This is moles per liter of oxygen at saturation. We also measured the temperature of the water at saturation, and using the temperature T, we can get a value for Henry's constant. So we have the molar concentration of oxygen at saturation, and we have our value for our Henry's constant. Using the relationship shown in the middle equation, we can rearrange to get a value for VI over VT, that is Vfrac. So now let's enter our values into the spreadsheet. First, we have total pressure, PT, and that's measured in atmospheres. Remember what that is. That should be very easy. We enter our bubbling time. As we discussed in class, we're not really using this. We'll talk more about time when we get to gas transfer kinetics, but Henry's law doesn't involve bubbling time, so we'll just enter this because it's good form. We'll enter the temperature that we measured at saturation and the milligrams per liter of oxygen that we measured at saturation. Now, using the equations that we just looked at, we can come down here and rearrange those equations to calculate the amount of dissolved oxygen we have at saturation for any value of Vfrac, that is VI over VT. So in this case, our Vfrac becomes our independent variable. We'll need to give solver some value to start with, just as a seed value. So because we don't know what our Vfrac is, let's start with 0.209. which is the Vfrac for oxygen at total room air. Down here in our CS cell, we're going to use the equations we just looked at and create a function that looks at the Vfrac and calculates the associated oxygen concentration at saturation. Now, if you've set everything up properly, the value displayed in this cell will be the oxygen concentration at saturation in milligrams per liter. What we're trying to do is to set this calculated value as close as possible to our measured value. This is our true value. This is the value we actually believe. And we're trying to get these two cells to agree as closely as possible by changing Vfrac. Just like we did in the last formula we worked with, we could start guessing for Vfrac. But for your assignment this week, we would like you to use Solver to perform this for us. If you set up Solver to get your calculated CS as close as possible to your measured CS by varying the Vfrac, it will find the Vfrac that corresponds to the fraction of oxygen you created in your beaker when you did your bubbling experiment.